Hello everyone, welcome back to our channel. My name is Edwin Hernandez, Grasshopper Specialist at ShapeDiver. In today's video, we will look why and how to optimize your Grasshopper definitions in order to reduce the computation time. We will compare the computation speed of widely used Grasshopper components such as solid difference or Loft with methods which output the same or similar result but at a fraction of the computation time. This is particularly useful if you are creating online product configurators, like a lot of our clients do, and you don't want your users to be waiting for a long time to get a response, to get a result from your Grasshopper definition. But before we get started, please remember to subscribe and to like this video as it really helps our channel. And if you want to know more about what you can do with ShapeDiver, make sure to check our website. All the relevant links will be down in the description. Let's get started. In this first part, we want to look into the Intersect tab of Grasshopper. This is a tab that contains a lot of Grasshopper components widely used by the developers. The problem of these components is that lots of them take a long time to compute, especially the ones that require solid operations. So if we look at the solid difference, solid intersection, solid union, and the majority of the components that you see in this shape tab, they require a lot of time to compute. Especially if the solids that you are giving them are free-form solids. So the free-form solids are the ones that come from a loft or that come from a ruled surface, from a sweep, from a pipe. All of these are free-form surfaces or B-wraps, which will take a long time to compute if then you put them inside a solid operation. That's why we try to avoid at all costs these components, and we try to replace them with simpler ones. So if we start to go to the left, into the region tab, into the physical tab, into the mathematical tab, all of these components start to become simpler and simpler in terms of computation. So if we look at the last one, so the mathematical one, there you are looking at operations that will take significantly less than a solid operation. The reason is because we are using simpler geometry expressions. So for example, if we look at the simplest one, the line expression is an expression that actually has a simple mathematical formula that can be applied. So if you wanted to do so, you don't need to even use this component, the line component, but you could use the mathematical expression. So here you can see the mathematical formula of a line, and then with the formula of two lines, you can compute the intersection between them. So here, for example, we have this graphic which shows the formula of one line and the formula of the second one, and with those two formulas we can compute the intersection of these two lines. That's why in Grasshopper, if we were to use the line intersection, it's a computation that takes no time to give you a result. Then when you start to use more and more complex geometry, your computation starts to increase. So if you want to keep your computation time low, you want to look into planar geometry. So of course the simplest computation that you can look into is points, then you can look into lines, planes, and then solids. So solid operations should be seen as the last resource if there is no other possible way of computing one section of your definition. However, there is normally always a way to make definitions faster. So for example, let's say that we need to create a parametric form similar to these ones, where we have some horizontal elements intersecting some vertical elements. And then we need to compute the intersection between these two so that we can actually create the notches where both elements will fit together. So for that, we have here an example. In the first one, as you can see, it's taking 7.5 seconds, whereas in the second one is taking just 2.2 seconds. If we look inside these clusters, we will see that the first cluster actually uses a solid operation, so a solid difference, and that's why taking the longest. So it's taking 6.4 seconds just to compute this solid operation. So here how it works is that it is simply using a graph mapper to create the form of these original circles. Based on that is that we can create the horizontal elements. So we just create an offset. We create a boundary between those offsets, and then we extrude those horizontal elements. And for the vertical elements, we get the original circles. We divide them based on the amount of vertical elements. Then we flip, of course, those points so that we can create actually the vertical representation of those circles. And with that, we can create again a solid that is the vertical elements, and we create the solid difference between these vertical elements and these horizontal ones. And we get, of course, the result that we expect with the notches. A simple operation that we could do in this case to optimize the solid difference is to simply do the solid difference with a single item of our solids, because at the end all of them are just copies that are rotated along the z-axis. So if we were to take just a single of these vertical elements, then that would already reduce our computation time by 6 times, as we are just operating into a single vertical element. However, there is a method where we can even avoid the solid difference component and create directly our curve with the notches without operating into solids. In the second solution that takes 2.2 seconds, we use a curve line intersection. So we went from operating in solids, in complex geometry, to operating in very simple geometry, which is just lines and curves. So here we can again look into the same graph mapper. Then we create just one single curve. So instead of creating all of these curves at the same time, we just create one. Then we extend it so that we make sure that there is always an intersection. Then we offset it based on our notch size. And then we take this base curve, so this will be the base curve for our vertical elements, and we are going to intersect them with the lines where the horizontal elements are positioned. So instead of computing the solids of these horizontal elements, we just compute the lines where they are located, based of course also in the thickness of our horizontal elements. And that gives us this couple of lines, so each couple represents each horizontal element. And then we do the intersection with the curve. Remember that a line is infinite. That's why we don't need to make our line intersect directly into the curve. So if we look at our curve and we look at our lines, they actually don't intersect physically as curves, but they do intersect as a line and as a curve. Then based on that intersection, we can use this component that is a pufferfish component called the point stream curve component. And this will get rid of these little pieces where the notches are supposed to go. And with these points that we have in our curve line intersection component, we can actually move them based on the depth of our notch. So in this case, we said that our depth is 10 units. So we move them 10 units inside our horizontal elements, and then we move them also up 10 units, which is the thickness of the material, to then end up with 4 points per notch, which creates the polyline that we can use for creating the final boundary of our vertical element. So we have here on one side the original curve with the gaps, and then we have the notches that we created with the points that come from the intersection. We just join these two curves, and then the last thing that we need is the other side of our curve, which is the same one but offset. And with that, we can actually make the connection. So we use the component called the connect curves component, and that gives us the final result without even using the solid difference component. Then we just need to make this a solid and to rotate it based on the amount of vertical elements that we set. So here in this example, we are just looking at the optimization of the intersection operation, but we could actually go further and optimize also the creation of the solids itself. So instead of going through a Brep, we could go directly into a mesh and reduce even more our computation time. But we will look into that later. Now we just focus on the intersections. The next example we have here is with the region operations. So the region operations use curves, and they normally compute quite fast, but based on the amount of curves you are operating on. So if you start to operate in a lot of curves at the same time, then these components start to take a long time to compute. In this example, we want to create a pattern. These patterns are normally used for jewelry especially, but as you can see here, you can also use these patterns for other kind of shapes. And the pattern we want to create looks like this. To create this pattern, we are populating a rectangle with points. So here we can see the points, we have our rectangle, and in these populated points, we create some circles that then we intersect with this grid of rectangles. So the first method that we're looking here of the region difference takes 5.6 seconds to compute. The reason is because we're putting as input these rectangles and circles directly without any previous sorting or without any previous checks. Whereas in the second example, it takes just 225 milliseconds. And the reason is because before we input these circles and rectangles inside our component, we first make sure which circles actually collision with our rectangle. So we have our rectangles here as surfaces and our circles. And then with this component, which is called the collision one many component, this one let us know whether the circle actually collisions with this rectangle, so that it is actually relevant for this rectangle to be computed with these circles. And then with that, we get a tree where each of these branches contains the circles that are specifically relevant for our particular rectangle. So we graphed also our rectangles, and then with the grouped rectangles and circles, we can reduce significantly the computation time of our definition. But now we have even a third option that takes half of our second option, and this option doesn't require of the use of any region difference. So as we said before, we try to avoid the use of any of these components, and in this cluster we will see how we manage to do so. So inside this cluster, we are again sorting our circles based on the collision with the rectangles, and then we just compute the curve intersection of these rectangles, these original rectangles, with the relevant circles. Then we shatter these rectangles, so we cut them through these points where they are intersecting, and based on the middle points of these shattered segments is that we check whether these points are inside our circles or not. If any of the middle points are inside our circles, that means this part has to be thrown away because this part is inside our circle, therefore it is not useful for us. And in that way we can get all of our rectangles with the specific part where our circles will be positioned. And in our second group, so we actually shatter our circles, and we do the same. We take the middle points, but now we do the check with the rectangles. So in that way we have our circles that are inside our rectangles and our rectangles with the specific section gaps where our circles get positioned. And in that way we can get the same pattern without ever using the region difference. So something that you may have noticed already is that optimizing our models actually take more components and take more logic than just using the simple region difference or than just using the simple solid difference. So for example, we went here from a single component operation to an operation that requires a cluster with loads of components and lots of logic. So what we have to have into account here is that what we want is not to save time when we are actually programming our definition, but where we want to save time is in the computation of the actual model. So it doesn't matter if it takes us double or 3 times more to develop our definition, as long as the computation time gets reduced as much as possible. Because at the end, these definitions will be used hundreds of times by users online in our product configurators, and therefore we don't want them to be waiting for a response from our definition. If you are just in the design process of your definition, then you may use all of these region difference, solid difference, etc., so that you can get a quick result and experiment with the design. But when it comes to actually converting this to a product configurator, then you need to go back into your definition and try to eliminate all of these components that take the longest with more optimized methods. Now let's go to the third and last of our intersect examples. This example is a golf ball. A golf ball may look as a simple model. However, the tricky part is to create the pattern that surrounds this ball. I have searched in the Rhinoceros forum, and here there is a thread where they look into how to create a golf ball. The main problem here, first of all, is to lay down all the circles that go around this sphere. But then the second problem is to actually create the holes as a solid. I have seen some of the definition that was shared in this thread, and lots of them use solid operations, which take a long time to compute. Here we can see the definition that we have created. Some of this part was reused from this forum thread, and basically this part just creates the base plane where our circles will go. So we can check here the little spheres that surround our main sphere, and then the idea is to create the solid difference between these two. In the first example we do that, and as you can see it's taking 25.5 seconds to compute. In the second option, which is a cluster, it takes 15 seconds to compute, so we have reduced by 10 seconds our computation time. But then we have a third option, which just takes 3.6 seconds to compute. And as you can see, all of them create the same result. If we check into the second option cluster, we can have a look at which methods we used here. So in this first cluster, instead of using the solid operation, we replace the solid operation with a split Brep multiple operation. So we just take our cut spheres, then we take the bounding box of our cut spheres, and based on the center of this bounding box, we test whether this bounding box is inside or outside of our main sphere. And with that is that we actually just select what is inside of our main shape. And on the other hand, I just take my main sphere with the cut parts, take the bounding box of each of these surfaces cut, and I take the biggest bounding box of all of these surfaces, so that we get our main sphere with all the holes where our little spheres will be positioned. Another option here, instead of using the bounding box, would be to actually compute the area of our surfaces, of our trimmed surfaces. And the biggest area would be the one that contains our holes, so this one. But the problem is that if I were to compute the area of these surfaces, just doing that takes a long time to compute. And we don't really need the exact area of our surfaces. We just need to know which surface is bigger to which one. Therefore, just using the bounding box is a good operation. But now let's have a look at our last cluster, which is the one that just takes 3.6 seconds. So how did we go from 25.5 seconds to 3.6 seconds? So in this case, we are using an even simpler operation that is called the Brep operation. So as I said at the beginning, as you move along to the left in your Intersect tab, the operations become simpler and simpler and they compute faster. So for example, first of all, we use the solid difference, which is to the complete right of our Intersect tab. Then we use the split Brep multiple component, which is also in the far right of our Intersect tab. But now we are going more to the left and we are taking the Brep intersection. So we are just taking our original sphere and computing the curves where these two spheres intersect. So here we can see all the curves, all the different circles. And then we use the surface split component, which is also efficient. So this one is also in our physical tab. So we're using two components from our physical tab. And with that, we can cut our main sphere and do the same operation that we did before. So we are again finding the bounding box of our surfaces and then taking the biggest one. And in the other side, we are doing also the same. We are taking the bounding box of our fragmented little spheres and just taking the fragment that is inside our main sphere. So as you have seen so far, there is always a better method to make your Grasshopper definitions faster, to compute faster, especially when it comes to intersections where different components have to interact with each other. Solid differences unfortunately take a long time because they normally first of all need to recognize which geometry you are putting inside the component and then make an operation over it. Whereas if you use other methods, you are actually telling the script which geometry you are actually providing. On one hand, the script has to figure out what geometry you are providing, and on the other hand, you are telling exactly the kind of geometry that you are using and just extracting information from the definition. In the next part of our optimization tutorial, we will look at how to create optimized meshes, optimized solids, and other tricks, tips. We will share some C# components. So if you don't want to miss out the next part of our optimization tutorials, please don't forget to subscribe so that you get notified of the next video. And if you have any questions, please leave your comment down below, and I will see you in the next tutorial.